Hi everyone, in this second tutorial we will talk about section 8.2 trigonometric integrals. First, I'd like to start with the following 5 trigonometric identities. These identities will be very helpful when we try to integrate trigonometric functions. These 5 identities are listed here, so have a look at here. The first one is the simplest one, and most of you will remember this, and the remaining 4s, the second and the third one, you can derive them from the first one, and the fourth one and the fifth one are sometimes called double angle formula. You can see cosine 2x term here, cosine 2x term here. We use cosine 2x to re-express sine square or cosine square. Alright, as you can imagine, this section is called trigonometric integrals, and we will integrate trigonometric functions. Most of the time you will see them in the product form, and there are a couple of different cases. So let's start with type 1 here, type 1, and here we will look at the integrals of the form some power of sine times some other power of cosine. And here, as you can see, I have n power of cosine and n power of, I have n power of sine and n power of cosine. And you'll see in a second we will decide what to do by looking at these exponents. Alright, here m and n are non-negative integers. Let's start with the first case. Case 1, either or both of these exponents are odd numbers. If one of them is an odd number, then we will do u substitution after we take one of the parts of that odd exponent. So let's say if the power on sine of x is odd, then we will factor one sine out and we will let u to be cosine and we will do u substitution. If the cosine has an odd power, then we will factor one cosine out and we will do u equals sine x u substitution, and we will carry out the rest of the calculations. So let's look at how this works on the following example. Here we have integral of sine to the power 4 times cosine cube. And here I have exponent 4, exponent 3, and the good news is cosine has an odd exponent. 3 is an odd number. So I will go ahead and separate cosine x times cosine square x, and I will let u to be sine x. So let's see how this works. So first I will go ahead and write this integral in the following form. This integral is the same thing as, this integral is equal to integral of sine to the power 4 x times, I'll go and do the splitting I just talked about, cosine square x times cosine x dx, right? So the odd power, I separated one of the powers in it and I kept the rest. Okay, then I will do u substitution, which is u equals sine x. In this case, I have to go ahead and find the u. The u will be cosine x dx, right? And this is good news because this part here, cosine x dx, I will use it for du, right? As you can imagine. Okay, so after this u substitution, let's see how we can write the integral. As I said, we will go ahead and use this part for du, and I know the replacement for sine to the power 4, that's nothing but u to the power 4. Then I have cosine square term. What's the replacement for cosine square? Here we have to remember the property of trigonometric functions. Sine square plus cosine square is 1. So in other words, cosine square is what? 1 minus sine square, right? Cosine square x is 1 minus sine square x. So here in this integral for cosine square, I can write 1 minus u squared. And remember, this remaining part was nothing but du. Now this is an easier integral to take because I can distribute u over, and I get u to the power 4 minus u to the power 6 du, right? And I know you know how to take this integral. once you take the u integral and put sine x back, you will get sine to the power 4x to the power 5x over 5 minus sine to the power 7x divided by 7 plus arbitrary constant c. So here again we identify the problem. We use the fact that we have an odd exponent. We separate the term with the odd exponent. We separate one power, and then we do the following u substitution, and everything else is quite standard. Alright, let me say a few words about the following two problems from level sign, number 2 and number 3. Here we have sine to the power 6 times cosine cube, so cosine has odd power. That means I will separate one power of cosine and then do u substitution. Alright, so here this integral is nothing but, we can take 12 outside, integral of sine to the power 6x plus cosine square x times cosine x dx. And when I do u substitution, u equals sine x, then du will be cosine x dx. So I can write this integral as 12 times integral u to the power 6. Remember, cosine square is 1 minus sine square, so it is 1 minus u square du. And again, you know how to take this integral, 12 times integral of u to the power 6 minus u to the power 8 du. Now I'll leave just like that. You integrate u and you put cosine back. Alright, let's look at the following problem. Here we have something a little bit different. Here we don't have sine times cosine, but still we can argue almost in the same way. So let's write this out. We have to remember what tangent was. Remember, tangent was sine over cosine. So this is integral 9 times integral. I have cosine square x term, and I will write tangent cube as sine cube of x divided by cosine cube of x dx, right? And I can cancel cosine square out. That will give me sine cube x, and I will have cosine x dx. Alright, again, as you see here, I have odd power of sine. I will separate one of the powers, and I'll try to do u substitution. So let me first write what we get out of this. So this is, when I do the separation, this integral is equal to 9 times integral of sine square x divided by cosine x times sine x dx. So which u substitution should I do here? As you can imagine, I will choose u equals cosine x this time, so that I can take care of this part here as du. That's the main trick we use. So here, if I choose u cosine x, then the u will be negative sine x dx. Okay, so after this substitution, I can go ahead and write this integral. Let me use that minus sign, pull that out, I get negative 9 integral of, alright, the first thing I have to replace is sine square. How can I re-express, how can I substitute for sine square x if I call cosine x u? Here again, I notice that sine square is 1 minus cosine square, so I can write here 1 minus u square divided by cosine x is u, and I have here I have du. Alright, so I can split this integral into two pieces. Negative 9 stays there. I will get 1 over u minus u du. Okay, so what's the remaining part? Let me continue here. This is equal to negative 9. What's the integral of 1 over u? It is ln of u in absolute value. Open a parentheses. Then I have negative u. What's the integral of u? Is u squared over 2 plus c. This is not the final answer. All I need to now is go back and put cosine back, so the final answer will be negative 9, open a parentheses, ln of absolute value of u, but u was cosine x, minus I have cosine square x over 2 plus arbitrary constant c. Alright, again here I use 1 power of sine. Let's go back and see how we worked out this problem. Here again I have odd power of sine. I separated one of the powers here and I use this part for du, and I did after this u substitution here, I got the answer without any problem. Okay. Alright, let's look at the second case now. Remember, in the first case we had sine times cosine, or like in the Weber sine problem we had sine times tangent, but the key idea was one of those terms had an odd power. Now in case 2 we will look at the remaining possibility in which both powers, both exponents are even numbers. In this case we will use double angle formula. We will re-express sine square or cosine square in terms of 1 minus cosine 2x or 1 plus cosine 2x. Here, as you can see, I listed those two identities back here. Sine square can be expressed in terms of cosine 2x like this, and we can re-express cosine square x in this form. Okay, these two identities are quite important, and they will be quite useful to solve some of the problems. Alright, so let's go ahead and look at the following problem. Here I have sine square and cosine square together, and I also have some limit points 0 and pi over 2, but as you can imagine, first I will forget about those limits. I will solve this problem as if it is an indefinite integral, and after that I will go ahead and put everything together. But here there's another tricky part about this problem. That's the following. I have listed here two identities, but there's another identity here I can make use of, and that's about sine 2x. So let me go ahead and write it up here, which will be also quite useful in some of the problems. Remember, we can express sine of 2x as 2 times sine x and cosine x, right? So just keep this in mind, and let's apply this idea to this problem. Here I have sine x squared times cosine squared x. What can I do here? First, I can combine these two terms and write sine x cosine x quantity square, right? But here I'm missing in the formula, I have this 2 and I'm missing that 2 here. So what I will do, I will put a 2 here and divide this whole expression by 2. So remember, this second power is above and on the top of this fraction. So in other words, I can write sine square times cosine square in the following form. I can write this expression as, so integral, and I will forget about the limits for a second. I have sine x cosine x times 2 divided by 2 to the power 2 dx. So this is the same thing as saying what? I can replace the numerator by sine 2x, so the numerator becomes square root of sine 2x, which I can write as sine squared 2x, and the denominator will be 2 squared, which is 4 dx. Now I got rid of one of the trigonometric functions, namely cosine, and I have only sine. But still I have this square here, right? Still I have this square here. How can I get rid of this square? Now I will make use of the first formula here. Alright, so by using this first formula, by using this first formula here, I can express sine square 2x. So remember now, instead of x I have 2x, so let me write it separately here. Sine square 2x is 1/2 1 minus cosine of, but instead of x I have 2x, so here I will get cosine of 4x. Okay, so if after this observation I can go ahead and write that last integral in the following form, I will get another half, so I can pull 1/8 out, and I will have integral of 1 minus cosine 4x dx, right? So this is nothing but 1/8, open a parentheses, x minus, what's the integral of cosine, is sine 4x over 4, close the parentheses, and arbitrary constant c. Okay, so this is the indefinite integral, but remember the problem was about this definite integral from 0 to pi over 2, so what should we do? We will go ahead and plug in those limits, so the final answer will be, let me write it here, final answer will be 1/8 x minus sine of 4x divided by 4, evaluated from 0 to pi over 2. When I plug in pi over 2 here, I get sine of 2 pi. Sine of 2 pi is 0, so I don't get any contribution from this part, but I get contribution from here. I get 1/8 times pi over 2, which is pi over 16, minus, when I plug in 0, the first term disappears. Sine 0 is 0, so I get nothing but minus 0. So the final answer is pi over 16. Alright, here when we don't have any odd exponents, we use double angle formula. Alright, so let's look at the following problem from the web assignment, the very first problem, which is very similar, and again I have only second power of cosine, no odd powers, which means I have to use a double angle formula. Alright, again in this problem I can pull this 9 out and forget about the limits for a second. Remember from the previous discussion, cosine square is nothing but 1/2 1 plus cosine of 2 theta d theta, right? So let me go back to the previous page to double check that formula. As you can see it here, cosine square of x or theta is 1/2 1 plus cosine of 2x or 2 theta. Right. By using that formula, I can rewrite that integral in this form. I can pull 1/2 outside, I get 9/2, integral of 1 plus cosine 2 theta d theta. This is an easy integral to take, so let me continue here. 9/2, integral of 1 is theta, integral of cosine 2 theta is sine 2 theta over 2. I will not put arbitrary constant plus c because this is a definite integral and I have to evaluate it from 0 to pi over 2. When I plug in pi over 2 for theta, sine of 2 times pi over 2 will be sine of pi is 0, so I get only contribution from this part, which gives me 9 pi over 4. Then I plug in 0, but the theta is 0, disappears, sine of 0 is 0, so I don't get any contribution from the second limit point, so the final answer for this problem is 9 pi over 4. So far we've seen at least 3 different problems from WebAssign. Actually you have another problem where you have to use a double angle formula, so you should be able to solve at least 4 of the 9 problems in your WebAssign 8.2. I will show you one more problem type, and after this you should be able to do it more than half of your WebAssign. The remaining half we will discuss on Tuesday in class. So let's look at the following problem, number 5. This looks like a trigonometric problem, and we have this sine cube term, but here we have to be a little bit careful because we also have square root of x running around. So what will be the first step for this problem? The first step will be, we will go ahead and get rid of this square root of x term. Alright, so I want to get rid of that square root of x term, and as you can imagine, I have to do u substitution for that. So let's say u is equal to square root of x, and I have to compute du. Du will be 1/2 1 over square root of x dx. And that's good news because that will help me to take care of this square root of x term at the denominator. Alright, so let's rewrite this integral. I can pull that 8 out. Then I have integral of sine cube of u. Then I have dx over square root of x. That's nothing but 2 du, right? So I can put du here and put that times 2 outside. So this all of a sudden becomes 16 times sine cube of u. And here, note that sine has an odd power, so I can split one of the powers, and I can write this as sine square of u times sine u du. And after that, I have to do another u substitution. So I will call something equals cosine u, but since I have already used u for this substitution, I will use another letter, let's say v, and I'll let v to be cosine of u. Then dv will be negative sine u du, and this will help me to take care of this last part of this integral. So after this u substitution, let's see, this integral is 16 times. I have first sine square of u, but I know cosine u, and now I have to use a trigonometric identity, namely the one sine squared u plus cosine squared u is 1, so sine squared u is 1 minus cosine squared u, but we label cosine u as v, so this first term becomes 1 minus v squared. And the last term, sine u du, is nothing but negative dv. So let me put dv here and put that minus sign outside. This gives me negative 16, integral of 1 is v, integral of v squared is v cubed over 3, and then I have arbitrary constant plus c. Now I have to go back and replace everything. First I will start with the second substitution and replace v. So I get negative 16, v is replaced by cosine u, minus v cubed is cosine cube u divided by 3 plus c. And this is not yet the final answer because I have to go and resubstitute for the first substitution and write u in terms of x, and in this case the final answer will look like this, negative 16. Remember, u was square root of x, so I get cosine square root of x minus cosine cube square root of x divided by 3 plus arbitrary constant c. Right? So this is the final answer for this problem. Alright, as I said before this problem, with this solution and the explanations, you should be able to do more than half of this assignment 8.2. There are a couple of problems you will have left, and those problems will be about secant function or tangent function or cosecant function or cotangent function, and we will discuss how to take integrals of those trigonometric functions, cotangent, tangent, secant or cosecant, on Tuesday in class, and you can complete the rest of the assignment after our class on Tuesday.